Stoichiometry gives us the quantitative relationship between reactants and products in a chemical equation. So, for example, if we know how much reactant we have, we can determine how much product we can make. Or if we know how much product we want, we can determine how much reactant we need to start with. In stoichiometry, we look at the proportions of reactants and products. So, for example, if we look at this equation here, normally we would read this equation as 1 molecule of iron 3 oxide reacts with 3 molecules of sulfuric acid, and we get 3 molecules of water and 1 molecule of iron 3 sulfate. However, we can also think about this in terms of moles. So we can think of this as 1 mole of iron 3 oxide reacts with 3 moles of sulfuric acid and gives us 3 moles of water and 1 mole of iron 3 sulfate. To give you another example, if we look at this reaction here, instead of looking at this in terms of how many molecules of hydrogen and nitrogen react to form a certain number of molecules of ammonia, we can think about this in terms of moles. So 3 moles of hydrogen reacts with 1 mole of nitrogen to give us 2 moles of ammonia. And we can write a ratio between any of these to show how many moles of one reactant reacts with how many moles of another reactant or other product. So, for example, if I want to go from moles of hydrogen to moles of ammonia, I can write this as 3 moles, and I'm going to abbreviate moles here, even though it's not that long of a word, the way we usually do. So 3 moles of H2 form 2 moles of NH3. Or I can write this, depending on whether I have moles of H2 and want moles of NH3, or I have moles of NH3 and want moles of H2. I can also write a conversion factor between moles of nitrogen and moles of ammonia. Or I could write if I want to write a conversion factor between the two reactants, I can write this as or I could write so I can get several different conversion factors from this reaction depending on what I have and what I want. When we do calculations in stoichiometry, there's 3 things we need, and these 3 things are all conversion factors. So the three conversion factors that we need are the mole ratio from the balanced chemical equation, the molar mass of the product, and the molar mass of the reactant. So these 2 we can calculate from the periodic table, and then we just need the additional conversion factor, the mole ratio, from our balanced chemical equation. So let's look at an example here. How much carbon dioxide would be formed if 10 grams of C5H12 are completely burned in oxygen. So when we say completely burned in oxygen, we're assuming we already have more than enough oxygen, which is likely the case if this is done in an open container because we have plenty of oxygen in the air. So the only way that we can relate C5H12 to CO2 is using the mole ratio. So what we're going to do is convert grams to moles and then convert moles of C5H12 to moles of CO2 using the mole ratio here. And then we can convert back to grams of CO2. So let's start with the 10 grams of C5H12. And if you look at your periodic table, you can calculate the molar mass of C5H12. That comes out to 72.17 grams of C5H12 per 1 mole of C5H12. And then we want to go from moles of C5H12 to moles of CO2. So we can do that using the mole ratio. According to our reaction, 1 mole of C5H12 reacts with 5 moles of CO2. Since we have moles of C5H12 to start with, we need that on the bottom of the next step so that moles of C5H12 will cancel out and we get 5 moles of CO2 on top. And then we want to go from moles of CO2 to grams. So we can calculate the molar mass of carbon dioxide, and that comes out to 44.01 grams of CO2. So if we look at our conversion, grams of C5H12 cancels with grams of C5H12. Moles of C5H12 cancels with moles of C5H12. And moles of CO2, cancels with moles of CO2. And we're left with grams of CO2, which is what we're looking for. So you put into your calculator 10 times 5 times 44.01 and divide that by 72.17. And you should come up with 30.5 grams of carbon dioxide that's produced. Okay, so let's try another one here. We have stomach acid, which is mostly hydrochloric acid, will be neutralized by magnesium hydroxide to form water and magnesium chloride. And we want to know how many grams of hydrochloric acid will be neutralized by a 0.5 gram dose of milk of magnesia. So if we look at our reaction here, you might notice it's not balanced. So we need to balance it. So let's go ahead and balance our equation here. Now, one thing that we have to recognize about this reaction is that the hydroxide ion does not stay together. So we can't balance that as a unit. We're going to have to balance the oxygen and the hydrogen separately. So we have 1 hydrogen, 1 chlorine, 1 magnesium. This 2 here applies to the entire hydroxide ion, which means we have 2 oxygens and 2 hydrogens. So we have 1 hydrogen over here and 2 over here, which means that we actually have a total of 3 on the reactant side. And we have 2 oxygens. On this side, we have 2 hydrogens, we have 2 chlorines, we have 1 magnesium, and 1 oxygen. So if we look through right now, magnesium is the only thing that's balanced. So hydrogen we have in 2 places on the reactant side. So let's start with the chlorine then. If we put a 2 in front of the HCl here, that gives us 2 chlorines. This gives us 2 times 1 is 2, plus 2 hydrogens over here, gives us a total of 4. So now everything is balanced except for our hydrogen and our oxygen. So if I put a 2 here, 2 times 2 is 4, 2 times 1 is 2. So now everything is balanced. So we want to know how much hydrochloric acid we can neutralize with a 0.5 gram dose of milk of magnesia. And milk of magnesia is the magnesium hydroxide. So we start with 0.5 grams of magnesium hydroxide. And if you add up the molar mass of magnesium hydroxide, that comes out to be 58.33 grams of magnesium hydroxide per 1 mole of magnesium hydroxide. And then from our reaction that we balanced, 1 mole of magnesium hydroxide reacts with 2 moles of hydrochloric acid. And then if we add up the molar mass of hydrogen and the molar mass of chlorine, that comes out to 36.46 grams of hydrochloric acid. So once again, if we look through, grams of magnesium hydroxide cancels with grams of magnesium hydroxide. Moles of magnesium hydroxide cancels with moles of magnesium hydroxide. And moles of hydrochloric acid cancels with moles of hydrochloric acid. So we're left with grams of hydrochloric acid. So if we take 0.5 times 2 times 36.46, and then we divide that by 58.33, that comes out to 0.625. I accidentally erased everything on here, but if you did that calculation, you should come up with 0.625 grams of hydrochloric acid that is neutralized. So we're going to stop here, and we will get some more practice with this in class.